My name is Praful and welcome to my presentation titled How Foundation Models Are Helping Save Our Planet. And we'll do a deep dive into the environmental AI. So, this presentation is based on an insightful 2025 paper surveyed by Chen, and Xi, exploring how large scale foundation models are applied to solve critical environmental problems. We'll begin with the agenda. So, here's what we'll be covering today. We'll begin with understanding why foundation models are even relevant to the environmental sciences. Then we'll walk through the historical evolution, how we move from physics-based models to foundation model era. Then we'll talk about the six superpowers of foundation models, the core application area they excel in, and will also look under the hood at how these models are actually built and trained. Then we'll pause to reflect on the key limitation and challenges these system still face. And finally, I'll share three personal reflections that I took away from this survey paper. So, um, so why foundation models? Why now? Right. This is the question. So, well, environmental science deals with incredible complex systems like weather, water, forests, climate, and different biodiversities. These are all interconnected, dynamic, and very data hungry areas, I would say. And additional models often struggle to deal with the complexity they have. Foundation models are trained on vast, diverse data sets, and they can predict like multiple outcomes, and they can adapt to new tasks and even fill in missing observation. And that too with a very remarkable, generalization. So in a way, there are like environmental multitaskers. Um, they are very flexible, very scalable, and very adaptable. They adapt to new tasks really quickly, and also they fill in the gaps that are in the observation really easily. So we'll be moving forward to how we evolved. So yeah, so how far we have come is like, we see, let's look how environmental models has evolved. So first we had this physics-based model, and traditionally physical simulation based on different fundamental equations were done in this physics 1.0. These were like interpretable, but highly rigid, and often they required a lot of simplification, and they were not good in the generalization process. Then we came into the data-driven machine learning, which could learn from the data that we provide without requiring full physical knowledge. This was powerful, but often became a black box kind of thing. Then we had the thing called hybrid physics ML models, where we combined machine learning and physical laws. And this led to a promising blend of interpretability and the flexibility that was often offered by the data-driven machine learning. And now finally we have foundational model. So these are trained on large multimodal data sets, and these are capable of performing multiple tasks with just fine tuning and prompting. So this is a true paradigm shift, and we are moving from single-use model, which was the process-based physical models, to very generalized and general-purpose model that are used in the environmental intelligence systems. Now, we have a foundation. We'll be talking about the superpowers of the foundation. That's so, yeah. Now, in this slide, I will just enlist each of them, and then we'll be moving forward and discussing them in the next slides one by one. So, these are like the six key application domains where they really, make their footprint, the foundation models. So, first it is the forward prediction, then it is the data generation where we generate the data, and then it is data assimilation, downscaling, model ensembling, and decision making. Let's unpack them one by one. So to begin with, we have forward prediction, and in this, it is probably the most intuitive one. These models are used for forecast future outcomes like temperature, water levels, or different kind of emissions. So they can integrate diverse data from different sources. Let's say data coming from satellites, sensors, and different kind of simulations. And we then predict how the environment will change based on that. So we predict the forward, like what is happening in the future. So model like Climax and uh, Pangu weather are already outperforming traditional climate forecasting tools while being, orders of magnitude faster. So they are performing really well. Like they're faster and they're better. Then we have the data generation. So environmental data which we have is very messy. Like we have cloud blocks in the satellite views. Sometimes the sensor fails, and some regions go unmonitored. And there we need some realistic synthetic data. So foundational models step in by generating that data to fill the gaps, like the clouds block when the satellite view. So we have models like diffusion stat that create high quality satellite images that have fully conditions on very small sparse input, and we that helping our research observe different places at time which we were not able to do, which has inclement weather, but we're able to do that. Now we go forward with data assimilation. This is about updating and prediction when new data comes in. So instead of retraining the whole model, what we can do is we can adjust the foundation model on fly using in-context learning. So, so when new sensor data comes, the model quickly recalibrates its prediction and just like updating. It's just like updating your route in Google Maps after a traffic alert. Next up we have is downscaling. So for most climate models that operates at very coarse resolution like 100-kilometer grids, but decision makers needs, logical insights, street level rainfall and, specific areas where there was some kind of drought. So foundation models can take broad low resolution input and generate really how high resolution outputs. They can effectively zoom in by learning to map course and detailed local behavior, all without retraining for every new location. So now we have with us is model ensembling. Here we combine different models like physical or ML based or hybrid model into a modular system that benefits from their collective strengths. Think of it like assembling a team. where each model brings their own strength. Uh, somebody is good at back end, somebody is good at machine learning, somebody is good at front end. So we are combining all the good parts of a model into a single part. The next we have with us is decision making. So finally, it's not enough to predict, but the model needs to present interpretable results that help people take actions. So foundation model like Climax I mentioned earlier don't just output numerical values, but they also deliver visualization, risk assessment, and scenarios tailored for human decision making. In different parts like management or conservation and different disaster planning. So now I'll be discussing how to build a foundation model. And here we have with us the first step is data collection, followed by architecture design. Then we do the training part, and then we fine tune the model, and then we evaluate on the unseen data by the model. So data collection. So in the data collection, what we do is um, this is where it all starts. Data from different satellite simulation and other different sensors all are collected and cleaned properly. And this in steps involves aligning different time frames and harmonizing the formats, removing the noise from the data and creating a very consistent data with diverse data set for training. Different coming from different sources basically. Then we have is the architecture, designing the actual neural network. These models must have multimodal data like text, images, tabular readings, and be scalable across region and tasks. So architecture like Fourier neural operators and multimodal transformer are often used here. So the ar- architecture design that are already present, um, that is used. Then we perform training, where during the training, model learns from different patterns in data after using supervised learning, like filling in missing parts of data, and to keep outputs um, scientifically valid. Training include physics guided constraint and multiple objective beyond simple accuracy. Then we fine tune the data and we do the prompt tuning. Here, the base model is adapted for specific tasks, do fine tuning or prompt tuning. And for an instance, like a model is trained globally, might be tuned to predict floods in a different part of the world, let's say South Asia, using just a very small data set or even few prompts. So we don't need to train that from scratch. We kind of use the transfer learning thing here. At the end, we have, which is the evaluation. Yeah. What we do here is we it have like what it contains is holding out data by different regional time, checking robustness. So basically splitting the data and we check the robustness in this and ensure physical consistency and evaluating the interpretability of the model. Model isn't useful if it doesn't work, you know, but like if it cannot be trusted, it is not useful. So what's still missing? What's the challenges ahead now? So the trust and explainability part is the most challenging thing. It's a big issue. We need to know why the model predicted what it did, how it predicted. So if it predicted a flood, why did it predict, right? Compute costs are very high, so the cost barrier is always there. Many labs cannot afford to train these models. And there, the model rare extreme events. So rare events like flood or wildfires are underrepresented in training because these can happen anything. We cannot predict a breakage of dam that easily, which will cause a flood or an overflow in river kind of thing. And the final thing is physical consistency. This is hard to maintain across all the tasks. Now, what are my reflections? So the three things that I learned is data will be the key. So data will define the environmental sciences future. And data is everything, I would say. Environmental science will increasingly be driven by the different quality of data which we have and the openness of our data sets. The second will be the physical laws must guide like the AI prediction. So physics isn't obsolete. It's more relevant now. Even the best AI needs to follow nature's law. The second last thing is we must democratize the access. Everyone, not just the funded labs, but everyone should be benefited from this models. So that will bring a lot of different minds in collaboration, and different people will collaborate and learn through this and can make any potential breakthrough in this field. So I have cited some references. Thank you so much for watching this video. And I would shout out to the publisher of this paper. This paper is available in the archive. You can follow this link and look into the paper. If you'd really like to read more, I have also published a full Medium article that breaks this down in utmost detail and including all the examples and references that were given in this paper. Thank you so much for watching. I hope you learned something out of this video.